Okay, so yesterday I said something wrong. So let me correct it first. About this box. I think this is what Guillermo was trying to point out, and I didn't understand. So this is not correct. The expectation value of TII, the time average of TII is not equal to 0 necessarily. It can be non-zero. A simple example is that take just a static system, like take a gas inside the container. So here it's just a time-independent system, a static system with pressure P. So obviously Tij is not 0 inside the box, because in here the stress energy tensor for a gas is going to look like there is some rho and some p sitting on the diagonals. Let me write it like this, and then I think there is a minus. So there are the other components are 0, but there are some spatial components which are non-zero in this static system. At some point in the middle of this box of a container. Similarly, in our photon example, photon in the box example, if I go to the middle of the box and look at the T mu nu of this photon, T mu nu of the photon looks like so the zeros component, it will be proportional to delta 3 of x minus x of t as usual. But then the zeros component is going to give me the energy of the photon. And then there will be a one component, which is minus E, and 0, 0. So let's see, there will also orthogonal components. It's not 0 because it is basically so it is P mu divided by P0 times delta 3 of x minus x, and then we know that the 4 vector is just E1, 1. So we get something like E minus E. So again, if I just look at the trace TII for a single photon at a spatial point, let's say this is the point x equal to 0. T photon traced at x equal to 0, and then if I time average it, that is not going to be 0, because there are points at which the photon goes through that point, and whenever it passes by, it has some non-zero trace, which is E. And it doesn't matter if it goes in this direction or in the opposite direction, because this is the component that is proportional to Pi, Pj, which will be P1 squared. So it always comes with the same sign. I think there will be a minus sign here to get the signs. But this is just an example of this gas. So if I put many of these photons moving in random directions, then the orthogonal elements cancel, and I get equal diagonal elements which are the trace. So so then what is the property? So in principle, if I have a time independent system or a periodic system which is localized, the special component of T mu nu do not have to vanish at every point in the system. What has to vanish is a different quantity. Let me first show you why the argument breaks down. So if I was looking at so let's for the moment consider just a static system. So dt is equal to 0. And then when we understand it for a static system like a gas in the box, then generalization to periodic system is not that difficult. So what I was trying to argue was that if I consider the I of Tij, that is by conservation, that is equal to minus d0 of d0j. And now either if the system is periodic and we take the time average, or if we assume that the system is static, this expression is going to be 0. However, the fact that di of Tij is equal to 0 does not imply necessarily that Tij is equal to 0, because I'm taking the divergence. So there are some of three terms in here in 3 dimensions. So I cannot just integrate this equation from one point outside. If it was just d1, if it were one dimension, the argument would be correct, because that would be d1 of t1 equal to 0. And then I could use the fact that t1 is 0 outside to integrate it and conclude that inside it is 0. But since we are in higher dimensions, then this is just a divergence of Tij is 0. It doesn't mean that Tij itself is 0 inside. Okay, so this doesn't hold. But there is one other property that does hold, and that's all that we needed to get the diagram that I drew. And that is, if you ask what is the average of Ti trace of T mu nu, or average of pressure for the whole localized system, or either average or just the total. So imagine I take the integral d3x of Tii over the whole system. This object is equal to 0 for a static system. And if we have a periodic system, then the time average would be 0. And the reason is that this is some trick that is useful also for what we are going when we talk about gravitation of it. So the reason is that this Tii can be written as dj of xi times times Tij. Minus integral d3x xi dj of Tij. Right, because if I take the derivative in here, there will be 2 terms, right? There will be, so this is, when the derivative acts on xi, it gives delta of ij, so I and j become the same thing. That becomes the trace term that we want. And then when dj acts on Tij, it gives me xi dj Tij. subtract. So this identity holds. Now, in the first term, I have a total derivative, and I have a compact system, so I can reduce this to a boundary term. And since this is a compact system, outside it, Tij is 0. So the first term is just 0. And in the second term, I can use the conservation equation. So the second term becomes integral d3x xi times d0 t0 I. Now, if it is a static system, d0 is 0. So again, I get 0. So this term will also be 0. Passing d0 is equal to 0. If otherwise, so say d0 is not 0, then we have integral d3x tii is equal to d0 of integral d3x xi t0. Because I can take this d0 outside of the system, since the boundaries of the integration are fixed. So the system is not flying away, it's contained in a finite fixed bound. So I get this expression. Now if I ask what is the time average, then if the system is periodic or is contained within some box, then the time average will vanish. Because then I can put time averaging here, which means that I take the limit t to infinity 1 over t integral from 0 to t dt d3x of tii, and this is limit t to infinity 1 over t 0 to t dt, and then I have d0 of something. But again, this term is a total derivative, so it reduces to the boundary term. So these are two finite terms, while t is going to infinity. So the time average goes to 0. Or if it's periodic, and I integrate over one period, the two terms that I get cancel. So for the purpose of the yesterday's problem, what it implies is that if I calculate the full T mu of the system, integrate over, if I take T mu and integrate over the whole system, there will be d3x t0 plus d3x tii, and but the time, if I look at the time average of that, then this term is 0, and the first term is going to be e plus n. No, m plus e. And then we can think about how this time average is realized by considering the trajectory of the photon, distinguishing the parts when the photon is in the middle of the box from the parts when it bounces back from the box. I think one would get the same answer if uh, if consider some standing wave in the box. It doesn't have to be I don't think that has to be with localized photon. No. Yeah, I think seems to me that even if I consider some standing wave in this box, then the result should look similar. Except that probably this diagram has a softer shape, like some oscillating behavior, rather than some spikes. And then the limit at frequency, yeah, I guess in some limit I just recover the single photon in the box. But I haven't checked this. That would be nice to check. To just consider a standing wave in the box and see how.
Like for one condition, the amplitude is not like always zero on the boundaries. Then it's like the photon is never like interacting with the wall or something like that. It's like just in the middle.
Well, imagine I have a spring. So this spring has, this is the deformation of this spring is a field, right? So this is x direction. The longitude.
But that is longitude, not the one
yeah.
transversal. So the boundary conditions like on the edges is different.
Doesn't matter. You can consider a string which has transverse oscillations, or let me draw a string. This is a string. This is a spring. You can consider both situations. The boundary conditions in both cases is a Dirichlet boundary condition, meaning that the deformations at so this is take this as x equal to 0 and x equal f. Then u at 0 because u at L equals 0. But it doesn't mean that you cannot have oscillating solutions, the standing wave solutions in here. I can deform this as a spring or a string so that it goes back and forth.
But so, what is the value? Like if in the previous case we knew that okay, when the photon hits wall, then you have like the peak. In this case,
take this. So this is a string that is attached. Let me put a little bump on it, which travels back and forth. It's like a photon. The boundary condition just tells you that it has to reflect when it hits the wall.
Okay, so it is like there are some peaks.
Yeah, let's see. Is there any qualitative difference? Yeah. So obviously you get some standing wave in here, which means that you can. I think you always get superposition of a left moving and a right moving wave. So that's the solution factor, right? So the U, which U omega and T, which is something like, I don't know, the form, I guess it will be sine of pi x divided by L times some cosine omega T. Something of this, where omega is just related to the stiffness. Okay, so you get a solution like that, and
you think the average is like constant?
the average.
But how do you define like, okay, the photon is interacting with the wall, like you have a peak, like how do you see it?
Yeah, I guess you're asking whether the T mu of this system is time dependent or not. Is that your question?
Just like to like thinking in the localized particle case, because it's like I can see it like that. Yeah, when the photon hits the wall, I see the peak. In this case, this is like because it's like there is always like the photon in the, because the photon is everywhere. It's always like the balls always are feeling the presence of the photon, I think, because that is the standing wave. It is but there is one condition that it is oscillating like an spring ring, everywhere all the time interacting with the walls.
Well, I think what you can do is that you can consider superposition of these standing waves to look arbitrarily close to a photon that moves back and forth. So you can really, but yeah, if you look at a single one of the standing wave solution, it probably has a constant time independent energy density. But if you superpose them, I think you can get a wave that moves back and forth. So you can hear like what you want is something that has its energy density being localized at some region inside the box rather than being uniform. Is that what you are asking for? So I think by superposing these standing wave solutions, you can make it arbitrarily localized, and then it looks like the photon that goes back and forth. Other question? Okay, so we want to do repeat all of the steps that we did in the case of a scalar gravity. We formulated the linear theory. Now we want to ask what is its phenomenology, and then we can compare it with the observations or experiments. And the easiest non-relativistic effect of the easiest relativistic new effect of this theory would be again the redshift. And the way that we can determine it is very similar to before. We can again consider a small clocks or small rulers that live on some background gravitational field, which is described by H mu. So we have little clocks, and so that the internal dynamics and time scales of the clocks is much smaller or shorter than the length scale of variations of the system. I want to ask what time do these clocks measure compared to the time at infinity, or like the coordinate time that we define here. So the easy way to do it is to go back and look at the point particle action. So we saw the point particle action because imagine that the different elements of those little clocks are point particles, except that they have some other interactions. So if I look at the point particle action, we saw that we can write it in the background gravitational field. It can be written as in this form, up to corrections which are higher order in H mu. And once we write it in this form, it's clear that the way the measurements of the clocks are going to be the same as if there was no gravitational physics, if we redefine new coordinates. Or in terms of the old coordinates, if we define a new invariant time, which is minus eta mu nu plus h mu nu times dx mu dx mu. So you can either think of it as the scaling of my coordinates or just the redefinition of the time. So this will be the time, or if I take the square root and define, let's just call this object g mu nu. Then this will be the time that the clocks are going to observe. So by analogy, we did that on gravity. In a scalar gravity, what we had was that in the case of dilaton, we had the point particle action, which was the square root of minus eta mu nu dx mu d sigma dx mu d sigma times 1 plus 5. And there we could define g mu nu to be 1 plus twice 5 times eta mu nu. So there we saw that the times that are measured in that system, this tilde, the time that clocks measure in this system are related to so imagine I have a clock which is at rest in some time independent background field. And there we saw that tilde is related by phi to the time at infinity, which was t. So here in this language is I mean it's the exact analog of that. If I plug in this expression for the metric and consider a clock at rest, then what this expression gives me is, so this is exactly equal to minus, well, let's consider some infinitesimal. This will be minus 1 plus 2 phi times eta mu dx mu. Because I'm assuming that the clock is at rest, so this expression, this is just going to be minus dt squared. And then I'm linearizing phi. This was the story in the scalar gravity. Here the difference is that if I want to do a rescaling of coordinates, define a new coordinate system that this is the same physics as if there was no gravitational field, then I had to introduce this, do a more complicated rescaling of coordinates. So it wouldn't be just, here it was just a uniform rescaling of all of the coordinates. But here I have this matrix or metric that rescales different components or different coordinates by different amounts. So it's a bit more complicated because the field has an index, but the idea is the same. So this was the graph. In particular, if I consider time-independent observers at rest in a time, if I consider observers at rest in a time-independent field, then I can try to write the analog of that expression. So now the theta in spin 2. That is now a square root of, since I'm talking about observers at rest, so I will have G00 times dt squared, and G00 is just one more name for eta 00 plus A00. But if you are considering weak fields, then we saw yesterday that H00 is going to be minus 2 phi. So this, and eta 00 is minus 1. So this is nothing but 1 plus 2 phi Newtonian times dt squared, which is 1 plus phi Newtonian times dt plus order phi squared. So what it tells us is that the result for gravitational redshift is the same in a scalar gravity and in a spin 2 gravity. The clocks work in the same way, the redshift in the same way, whether the description is in the scalar gravity or the relative gravity. The situation for rulers and distances is different because now, if I want to measure, so now imagine I'm considering not an observer at rest, but somebody who is moving, or I'm talking about rulers. So in general, I'm talking about the word line in this background field. Now I can divide this word line into small elements and consider good clocks that measure time along this word line and add them up together. So what they are going to measure is the integral of this tilde. And now, since this observer is moving, then the result in the two is generically going to be different for the two observers. One of the lengths along this observer, which is the time that the clock measures, is going to be dependent also on the ij component, because now there is non-zero dx, non-zero dxi, dxj here. So there are two different answers for the lengths of these word lines in general. The second question that we can ask is about which is very related to what I was saying, is about the motion of the particle. In some background field. So we derived the equation of motion coming from this action yesterday. Now it would be good to rewrite that equation of motion in terms of this new variable tilde that we define, because that's the time that the onboard clocks on a spaceship are going to measure. So that's the one that we can call it a more physical time. But that's what the clocks measure. So if I want to express, so let's remember how the equation looks like. That d by d sigma, and then I'm going to write it in terms of this combination that I call G mu nu. So the expression was that G mu nu divided by essentially d tilde d sigma times dx nu d sigma equals 1/2 d mu of the alpha beta dx alpha d sigma dx beta d sigma divided by again d tau tilde d sigma. Where is the tau tilde? The sigma is just basically is given by this expression. It's this usual square root that we always get. So if I multiply the whole thing by, or divide the whole thing by another factor of lethal theta by sigma, then this equation becomes, looks simpler. It becomes, looks like this. And now we can again ask what is the motion of the particles given some background field. Imagine we determine the background, what the background field is. We can ask how do particles move. This equation is called the geodesic equation. But I think we will see later why it is called the geodesic equation. So we already checked the motion of non-relativistic particles in background field. In fact, we used that to fix the relation between H0 and Newtonian potential. So we took the non-relativistic limit of this equation, and by requiring that it reproduces the Newtonian limit, the right Newtonian force, we fix the relation between H0 and phi Newton. Okay, now what we can ask, one more thing that we can ask is how would non-relativistic particles move? Before that, let me still consider the general case, but assume that we have a static field.
Static what? Static?
Static field.
Okay.
Which means that d0 is equal to 0. Or d0 h mu nu is equal to 0. And again, I'm setting h0 I equal to 0.
Can you repeat what is that?
What? No, I'm just assuming.
Okay.
Just consider this special situation that we have a static. It's an important situation because, for instance, you want to understand the light bending by sun, as in the homework problem. Then you can treat the field of the sun, gravitational field of sun, as a static field, right? It doesn't be on the time scales by which the light passes by the sun. The field doesn't change much, so you can take it to be a static field. Now, if the time derivatives are zero, now if I look at the zeroth component of this equation, when mu is equal to 0, then the right-hand side vanishes, right? Because it will be d0 of g alpha beta. Remember, g is just eta plus h, so eta is just a constant whose derivative vanishes. It becomes d0 h, and h is assumed to be time independent. So we get the derivative of this object is equal to 0, so that gives us a constant of motion. And since we are in the gauge in which H0i is 0, then G0i will also be 0, because H0i is 0. So what we get is that G00 times X dx0 theta tilde is a constant that I call E over N. Let me also call X0 T. So dt over theta tilde is E over M G00. Let me also put a minus on because G0 is negative. And this is approximately E over M plus order H mu nu or H00 correction. Okay, so what else we can do? We can look at the our definition of tau tilde, which tells us that G mu nu dx mu d tau tilde dx mu d tau tilde, that is equal to -1. That was just our definition of tau tilde. And in this particular gauge, that is going to look like G00 dt tau tilde squared plus dij dxi d tau tilde dxj d tau tilde equals -1. So if I use this expression for dt by d tau tilde, what I get is di dij dxi d tau tilde dxj d tau tilde equals d squared over m squared G00 -1. Now imagine I make the energy very large. So I make the particle to be more and more energetic. It becomes ultra relativistic, right? The limit of E over M going to infinity is the limit that we get a photon or a null ray. Still, I keep H to be a small. So these are independent things. So what happens is that this dx over theta dxi over theta tilde squared, that becomes E squared over M squared plus order H correction. This is the limit that E over M is much larger than 1. So I can neglect this one piece here.
Sorry,
Yes.
why the cross terms are cancelled?
Uh, you mean when I and J are not the same? No, they are not cancelled. They are in here.
Okay.
Because this Gij is just eta J plus Hij,
Okay.
right? Eta Ij is diagonal.
Mm-hmm.
So what remains is Hij times that.
Mm-hmm. Yeah.
They don't cancel. They are there, but for my I mean, for what I'm going to say next, that I need only the zeros order because I'm going to look at the I component of this equation. So imagine now I go and look at the I component. So we are considering, let's consider a weak field approximation. Then this term, of course, the derivative of H alpha beta is 0. So this is really just the I of H alpha beta. So this is already linear in H. So in what multiplus I can plug in the zeros order in H value. So what does it give me? It gives me so I have 1/2 dI of H00 times dt d tau tilde squared, and then I have dI of H mn dxm d tau tilde dxm d tau tilde. What about the left-hand side? So on the left-hand side, I have two terms. One is Gij times the acceleration, and then the other one is d by d tau tilde of Gij times dxj d tau tilde. So this term, d by d tau tilde of Gij, is equal to so So why does Gij depend on tau tilde?
I mean, for the static case, it should not.
Even in the static case, it does depend. Yes. At least if you are not considering non-relativistic particles. Because, so again, remember what is the configuration. We have a particle that is moving in this h mu nu field. Right? This h mu nu field is just a function of x. It's time independent. However, the particle is moving. So when I say d by d tau tilde of Gij, this is just d by d tau tilde of Hij. But Hij depends on tau tilde through its dependence on x, because the x that sits here is x of tau tilde. So this is d x k d tau tilde by chain rule times dk of Hij.
So in the first in the graph, h mu nu is static in the sense that it's field. I mean, it's like the particles are static, something like that.
The particle?
No, I
Which
mean
part?
like the field.
The field is a static. It doesn't change in time.
Yeah, so the
So
derivative. In that case, the derivative with respect to time is 0.
The derivative associated t is 0. So the t of h mu nu is equal to 0.
In that other case,
But the tau tilde of h mu nu is not 0 because the tau is the derivative along the trajectory.
Okay.
So imagine the following situation. The temperature on the Earth, it has, I don't know, imagine something relatively constant for some time scale. Short enough time scale is relatively constant. If you travel very fast from different parts, like from the sea level to the mountain, you see a temperature difference. That's not because the temperature changes with time, it's because your location changes.
Yeah.
Okay.
So here is the same thing. The field itself is constant, but you see different values because you are moving.
Okay. Just one thing. I don't know. Because I haven't seen GR before, but because of the things that we are seeing, it feels to me that H is something related to the metric. Like it's something that gives you the right way to measure the time. Like the thing that gives I don't know the right expression for measuring the length of a moving particle. Is that?
Well, yes. I mean, we discovered it in a different way. So we saw that if we want to describe gravity using a spin-2 particle, it naturally acts at a linear level at least. It naturally acts like the metric that tells you what are the distances.
Okay, but it's just like an approximation.
Well, a linear order, that interpretation is correct. Whether it remains to be valid at nonlinear order or not, that's the question that we are going to ask next week. But a linear order, yes, that is how it works. All right, so there is another term. that really belongs to the right-hand side, because we want to see what is the acceleration in terms of the derivative of the field. So by the way, the acceleration itself would be 0 if we didn't have any field. If Hij or h mu nu was 0, then the second derivative of x with respect to tau would be 0. There would be no acceleration. So here, this Gij can be set to be equal to delta Ij or eta Ij. So I can ignore h in this first term because it's already proportional to the acceleration.
I didn't get the logic. Can you please explain it? I mean, first, why the acceleration is 0 if this is 0?
You see every term in this equation except the first term contains derivatives of Hij.
Okay, yes.
Or derivative of h mu nu.
Yes.
So if I set h mu nu equal to 0,
yes.
what I get is that the acceleration is going to be 0. So acceleration itself is first order in the field that I have.
Yes.
And this is what we expect. If there is no field, I move on a straight trajectory. Yes. So there won't be any acceleration.
Yeah.
Therefore, this is proportional to h. We are linearizing h. So in the coefficient, I have to ignore factors of h. So this Gij, remember, it's just eta Ij plus Hij.
That's 0.
But since this is already first order, I should drop this h.
Yes. Okay.
Why do you say that it's first order?
Why do I say the acceleration is first order?
You only found that it's 0. It could be second order, it still be 0.
Oh, right, yes. It could be 0. At least it is first order. Yes, it could be 0. It could be 0 to all orders. Okay. So what we have is d2 squared is equal to some lengthy expression. So it's 1/2 and di of h00 dt dot tilde square. One thing that I can do is that we can call derivatives with respect to tau theta with dots, just to simplify things. So that x I dot is e by d tau tilde of xi. So now I get t dot squared plus di h mn xm dot xm dot minus twice minus twice dot dot some equation like this. So this is a somewhat complicated equation.
But how could you drop the Gij in this equation? Because you get H, all the H is there. How could you drop the Gij?
You mean the one that multiplies
with
the
acceleration.
acceleration?
Yeah.
Well, I'm saying that the acceleration itself is at least first order in H mu nu. So if I keep the, so in Gij you have Hij plus Hij.
Yes.
So if you have this term, there is delta Hij plus Hij times dx d2xj d tilde square.
Yes.
Right?
Yes.
Now I'm saying that this term itself is order h or smaller.
How do we know that?
But by looking at this equation, if you set h to 0,
Yes. Then all terms are 0 here, right?
right?
So
it cannot have any zeros order terms in it. It has to have at least order.
Some order 1,
Yeah.
yes. Okay. So we are
Therefore,
dropping it. Yes.
Yeah, therefore this term will be at least of second order.
So derivatives on H are not zero order, for example. Are at least not first order.
Say it again.
Like derivatives on H are not first order on H.
They are.
But we are not taking out first order reference in it. For example, the IH00 is not is at least is not first order in it.
Yeah, it is first order in it.
So we are dropping second order.
Yeah.
Okay.
So yeah, this is so given some background field. Okay, so one other thing is that now in here I can, since I have factors of h, then for x dots I can plug in the unperturbed values. So if I'm considering some trajectory, some like trajectory, which has some high energy E over m, then these x dots for this exercise, we can plug in the values which are zeros or in H, as we were doing before in small angle scatter. So because we already have factors of H behind. So these terms, as you can see, these terms are all of them proportional to E squared over M squared. So this is tau dot squared, which is E squared over M squared. And then these are, then distance depend on the direction of the velocity. If I assume that x dot x xi is equal to over xi. If I assume that the particle is moving along the x direction, so x of t at zeroth order is going to be just t times x hat or x hat 1 if it's just moving along x direction. Plus some corrections that come from the fact that it's moving the gravitational field, and then this expression simplified. So we get the accelerations. We cannot plug in the first component of x in here. So we can use the fact that the only non-zero component of x I dot will be x I dot will be just delta of I and 1 plus order H correction. Right, so this is the idea that this, so imagine if I'm considering some scattering problem, then this is x and this is y. So I'm talking about the trajectory which, if I'm perturbed, it moves along x, but then in the field it will be perturbed. So to zeroth order in the background field, x dot is just going to be equal to 1, because now I'm considering the case in which E over M is much larger than 1. So from here, sorry, x dot is not going to be 1. From here we will get that x dot will be E over M. So we are assuming E over M is much larger than 1. And then this equation simplifies, because then we will we'll pick only some special components. Okay, I think I can leave the rest to you to do it for the homework, because that would be basically what you are asked to do in homework.
But I have a question here. This form of xt, this is t times x1. How do you get it? I don't understand.
Oh, I just got it from here. So I'm saying that, imagine, so the zeroth order in H, we had this expression.
Yes.
That just comes from the definition of tau.
Yes.
Now, if I assume that the particle is moving in one x direction, for instance, that somewhere all i's reduces to just dx1 d tau tilde square equals E squared over M squared.
Yes.
So that means that yes, it's dx1 d tau tilde is E over M, and then you can ask what is dx1 dt, that is d tau tilde dt times dx1 d theta tilde.
Yes.
By theta tilde by dt is m over e
Yes.
from there.
Yes.
So then it becomes 1.
Yes.
But I really wrote this because if you consider an ultra-relativistic particle that moves along x direction, one direction, its equation of motion is x equals t.
Yes. Yes, I mean, assuming that it moves at the speed of light, right?
Yeah. But that's when we consider ultra-relativistic particle, it moves almost at the speed of light.
Yeah.
Of course, there can be a constant. This is assuming that it goes through x equal to 0 at t equal to 0.
Yes.
Okay, so this, so we can determine particle trajectory in this theory. Interestingly, it's going to be different from what we get in the case of a scalar gravity. So in the scalar gravity, you got 0 for the bending of light, but here we won't get 0 anymore. The force term doesn't disappear as we make the particle or ultra relativist. Okay. So is there any questions so far? So the last topic in this discussion would be gravitational waves. So this is almost identical to what we did in the scalar case. The only difference is we should do some manipulation of indices. But the ideas are all the same. We consider some system which is time dependent. Now we have some wave equation. It's a bit more complicated wave equation. We have time dependent sources. We have a field that has the equation of motion, which is D'Alembertian plus some other terms because T mu. I guess here I have 16 pi g. And since the sources are time dependent, there will be a time dependent solution at large distances. That solution looks like a wave that propagates. So again, there will be, as the function of r, there will be some distance, which is over the 1 over omega, or c over omega, where omega is the frequency of the system. And when r is much larger than this 1 over omega, then we have a solution for h mu that looks like that goes like a over r e to the minus I omega t minus I. In fact, we can choose a particular gauge in which the equation looks almost identical to the scalar case. So I can define this new variable psi, which is I think h mu nu minus 1/2 eta mu nu h, where h is just a trace. And for that variable, the equation of motion is almost identical. So we have just many copies of the same equation that we had for a scalar. And then we can find the solution for psi mu nu to be, I think, 4g divided by r integral d3r times t mu nu of t minus. So this retarded potential that we were talking about the other time. So we get the retarded solution if we have a system which has some characteristic frequency that gives us some waves that at large distances they look like this. If we consider some local observatory, for them these waves look like plane wave if we are talking about distances. So if we are on Earth and there is LIGO, these waves around this system, which is much far away from the emission point, the waves look like a plane wave. There is some constant, another constant, let's say a bar d2 minus I omega t plus I k dot x. This is a plane wave. We can calculate what is the energy inside the plane wave using the quadratic action that we found. And we can calculate the amplitude using our retarded solution. And once we integrate it over the whole sphere, that gives us the total power that is being emitted from the system. And if you are in the non-relativistic regime, when the size of the system, or omega times r, which r is the size of the system, is much less than 1, or equivalently, the velocities are much less than 1, then we can do multiple expansion. The leading term in this expansion is going to be the quadruple term. And then we get the quadruple form. So unlike the dilaton gravity case where the leading term in the expansion was a monopole term, here the first term in this non-relativistic expansion is quadruple. Yeah, which gives us an accurate description for many astrophysical observations.
Why the first order is quadruple?
Well, the first term in this expansion, so if I'm taking omega r much less than 1, so what we were doing was that we were taking this and we were expanding this. So this was t. We were going to look at r much larger than r prime. So this argument is t minus r plus r hat times r prime plus order terms of order r prime squared over r that we can draw. So then we were expanding this by taking time derivatives. So we were expanding this expression we just the Taylor expanding in terms of this cycle because this is much smaller than that. So we're saying that is an expansion in powers of omega r, right? Because it is 1 over n factorial dt to the n of t mu nu of t minus r and r prime times r hat times r prime to the n. So this term is over the r, the size of the system to the n, and this is time derivative, so it's over the omega to the n. So this is omega r to the n, which is the velocity to the n. The leading term in this expansion, if omega r is much less than 1, the leading term is the first term in the expansion, which is the zeroth derivative. So therefore, we get to leading order, we get psi mu nu equals 4g over r integral d3 x t t mu nu of t minus r and r prime. Let me write it here. So this is the first term plus order order b or cross corrections, which is suppressed by powers of e. So I write it as let's say I have n equals 1 to infinity. So this is n equals to 0 in that expansion, and then the relativity higher order. This was t minus r. These terms are suppressed. This is the leading term. Now, why is the leading term a quadruple term? The reason is that if I look at this faraway field, as we said, this field h mu nu has some gauge symmetry. Has this linearized diff invariance. So for a field that moves or propagates, this plane wave that propagates along k, you can use the linearized diffeomorphism to bring it into a special form, which is this spatial transverse traceless form. So using the linearized diffeomorphism, this Hij can be brought into a form that has zeros everywhere, except in the so if I now consider some waves, plane wave h mu nu, which is a e to the minus I omega t plus I k dot x. Then using the diffeomorphisms, we can bring it into a new form. And let's imagine k is along x. K is x hat times omega. Then you can bring it to the form in which it has zeros everywhere except in this by z block. When you have h plus, and h cross, you only have non-zero components here and here. So h, this is minus. So you will have h y equals minus h c c equals h plus, and then you have h y z equals h prime. So you can bring H to this form. Then you can see that once you bring it to this form, you can ask what happens to psi. So related to psi, you see that these H plus and H cross, these components, they are basically related to the same components of psi, because these are traceless components. And to define psi, I have added something to the trace. So once I look at the traceless contributions, it wouldn't change anything. So this psi and H, once I look at these components, they are going to be the same. In other words, if I look at HYZ, that is going to be the same as psi YZ. And if I look at HYY minus HCZ divided by 2, so this was H cross, and this was H plus. This is going to be the same as psi YY minus psi ZZ divided by. Alright, so we are going to look at the YZ and this combination of this psi, which is given by that formula. In particular, we are interested in IJ component, in a spatial component of psi. So that will be TIJ. Now you can do some simple manipulation similar to what I did at the beginning of the lecture to show that this to relate this integral TII. So you remember we had the volume integral of TII in a compact system, and we related this to E0 or something. So a similar manipulation can be done to relate integral psi ij from that formula let's keep the picture. So let's look at, let me just do it here. If I want to look at psi ij, then there will be an integral of t ij, right? Then you can do some similar manipulation to relate the integral of t ij to second time derivative of integral of r prime I, r prime j times t0, 0. So that you can find in the notes. I do it explicitly. But it's almost the same idea as what I did here. You can use conservation equations to relate the integral of ij components to integral of 0 components. So therefore psi ij is related to this quantity, and then if you look at these particular components, those are related to traceless parts of this matrix. That is the traceless components of this matrix. This is r prime times r prime I, r prime j minus 1/3 delta ij r prime squared t0, 0. That is what is called the quadruple moment. So that's how you get a quadruple formula as a leading term.
Just because of the gauge.
Because of, well, because of something, I don't know because of what.
Just because you just choose the gauge to have the
Well, at the end of the day, the result is a physical result. I just use the gauge transformation to simplify the final result. But once you derive the total energy that the system loses, like the power, that is some physical observable quantities. So when I say that the power is like G over 45 times Q ij triple dot square, that has nothing to do with the gauge choice, because QI resistance is something that I can calculate. I can take its time derivatives, 3 times derivatives, and that gives me some result. I can go and observe, measure it. So yeah, I use the gauge transformations to derive this in the formula. But at the end, the result is the gauge independent. Other questions? I try to be very explicit in the notes about these manipulations, but if there are some questions, you can ask me. I don't know, Friday or tomorrow.
What?
I don't know.
What? That should be